This is the OrbitPoint Gravity Engine video. In Gravity Engine 4.0, there's a new demonstration scene in the Gravity Engine scenes, demos, scenes, OrbitPoint scene. And if we open that scene, we get an example of the new OrbitPoint feature. And what the OrbitPoint component does is it provides a way to locate a point on an orbit based on what type we wish, and we have a variety of choices. We can choose for an ellipse, apoapsis, for a hyperbola or ellipse, periapsis, a particular radius along the orbital path, the ascending or descending node, a fixed time ahead of a reference object, or a specified phase, and that can be made interactive using the phase from mouse. So in this scene we have a spaceship. It has an orbit universal. We're currently using a non-inclined, slightly eccentric orbit to help demonstrate the capabilities. The scene also has a translucent plane that is along the equatorial axis of the central body. That'll be useful when we come to our discussion of ascending and descending nodes. So if we just, with our orbit point here, it's just positioning itself, and there's a marker here which has a capsule on it, which we'll see in the scene. And so we begin with it just set to apoapsis, start the scene. And as you would expect, you can see we have the capsule placed at the furthest away point of the orbit. We can interactively, without stopping the scene, flip that and make it come to the periapsis. If we want to locate this object at a particular radius, provided that the radius is inbounds for the orbit, then we can pick either altitude first, in which case it takes the lowest phase value that has that altitude, or altitude second, in which case it picks the same distance on the other side of the orbit. We'll handle ascending and descending node at the end. Next, what we'll do is we'll look at phase, and here it's at a fixed phase of 20, and if we change that to 45, it moves to 45. And finally, we could choose phase from mouse. And then what happens is the OrbitPoint script, because we have mouse control enabled here, will detect mouse clicks and turn them into an angle with respect to the central body, and then put the phase of the object at that angle. So as we click and drag around, we can essentially drag the object on the orbit wherever we wish. We started with an elliptical example, but we can very easily change this spaceship to a hyperbola, restart the scene, and we can see that when we click, our mode reset. So we're now currently at a particular distance. And apoapsis is not valid for a hyperbola, so it's giving us a whole bunch of warnings. So we'll go to periapsis. The warnings stop. We have it located at the periapsis point. We can pick a particular altitude. We can specify a phase, or we can do phase from mouse, and then click and move the point along the hyperbola. So that leaves us with three of the types we haven't discussed. We haven't discussed the fixed time or the ascending and descending node. So let's deal with fixed time. So when we use fixed time, we need to do it with respect to a particular spaceship. And then when that mode is selected, it will say 20 time units ahead of where the spaceship is in the orbit. So if we take our spaceship and put it back into an ellipse, just for simplicity, and then press play, what we'll see is that the orbit point stays a fixed time ahead of the spaceship. And we can change that time interactively and make it a little bit closer, or a lot closer, just one time unit ahead. And that's all as it should be. So now let's take a look at ascending and descending node, and this starts to get into a technical detail which is worth being aware of. And depending on how closely tied your project is to real orbital elements, may be an important detail for you, or may be something that's not a big concern. So we've picked ascending node, which is intended to be the node at which the inclined orbit goes through the equatorial plane in the positive z direction. And so in order for that to make sense, we'll have to give our orbit a little bit of inclination, so we'll do 20 degrees. So now when we go ahead and press play, we can see that there is in fact an inclined orbit. It comes above the plane and below the plane. We have placed the marker at a node of the orbit, but in this view it looks as if we're descending as we go through that orbit point. But if we look at the spaceship and the z component of the spaceship, we learn that it is actually at positive z, so it did go through the equatorial plane in the positive z direction, so this is the ascending node in that context. But why does it look backwards? Well, it looked backwards because we've set our camera at -z, and we've set our camera at -z to account for the difference between Unity's left-handed coordinate system and the traditional right-hand coordinate system that the language of orbital mechanics and most of physics is done in. There are different choices for when you pick an x, y, and a z axis, which particular directions they face. And different programs have adopted different conventions. Blender is right-handed, Unity is left-handed, DirectX I can't remember, but it has also made a choice. And so as you go from tool to tool, this is the kind of thing that you may encounter. And in this case, we encounter it in the context of orbital mechanics. This is enough of a topic that on the nbodyphysics.com page, I've created a discussion of it, and you can find this under the orbital elements in Unity's left-handed coordinate system. And so here is the standard physics definition of all of the orbital elements. So the motion is clockwise, positive inclination is in the positive z direction in the xy plane, omega is counterclockwise with respect to the z-axis, and so forth. So there are a couple of choices discussed in this webpage about how you can fix this. First of all, depending on your game mechanics and whether you're tied to having the exact visuals that correspond to the orbital elements, you could just simply say, well, I know for the orbit point that if I really want to see the node descend, I should pick the opposite of what I want. So the ascending node will look like the descending node, and you just make that conversion when you pick the orbit point. The alternative would be to leave Gravity Engine working with its right-handed XYZ, but when that is pushed into the Unity left-handed coordinate system to do a reflection on the Z coordinate. And so we can do that through a fairly sneaky technique. Gravity Engine allows you to change the origin and use a transform to reposition. This transform also allows you to apply a scale. So what we can do here is in the scale factor, we can set this to -1, and that'll do a Z reflection. So with this enabled, what will now happen is what was previously a positive Z value in the world will now become a negative Z value. And so here we have what we expect, which is we have the ascending node at the correct location. It appears to be coming up in the view, and it matches the diagram that you would get in a physics textbook. The only thing that you need to be aware of if you do this is if you're taking a world coordinate value and mapping it into Gravity Engine, the Z coordinate needs to be flipped. If you keep track of that, then it'll all look exactly as it should in orbital mechanics books. Or you may decide that you can just adapt to the directions being reversed in the use of the orbit point. That concludes the overview of OrbitPoint. It's a pretty handy way to put an object somewhere on an orbit. Thanks for watching.